right, hello everyone. Today we're going to do our final new topic of the unit, which is integrals of inverse trig functions. This is also the last set of new rules that we're learning about, or in terms of integral rules that we're learning about. Okay. But before we get into these rules, I want to kind of help us see that kind of like a bird's eye view in terms of, especially amongst rational functions, how to decide between the rules, because some of these rules can look some of these problems can look very similar, where it's tough to distinguish between, is it an expansion power rule? Is it a U substitution? Is it long division synthetic? Is it what we're going to learn today, arc trig? And I created a document that I put up on the website just this morning, maybe last night, this morning, where I created just examples of very similar looking rational functions. And I want us to be able to see the distinction by comparing the degrees between numerator and denominator to help us decide what rule to apply. So I have this document here. I'll go over it. You guys don't have it in front of you, but you can always, we'll come back to it and revisit this, and it's also on the website as well. Okay, so if you look at this expression, right, versus this one, they all have x's, numerator and denominator. And if you just look at this briefly, it all looks similar, right? Like it's tough to know what rule do we use. Is it just a guessing game? But I want to kind of help us distinguish some of the things before we jump into these last set of rules. So usually we're going to compare between numerator and denominator, and that's going to help us clue us in as to which is going to be the path that we want to follow, except for the first one. Okay. If there's only one term in the denominator, that's a good indication that we want to split into individual terms, conquer and divide. We're going to split into individual fractions, and then we can treat each like a separate problem. Maybe it's power rule, maybe it's natural log, but we're able to kind of split up into individual terms. Okay, now this only works if your numerator and denominator are within the same family of functions, right? If your numerator is trig or natural log or exponential e to the x, and your denominator is polynomial or rational, we're not able to, right? This doesn't quite work out, or this rule doesn't quite work out. Okay, but as long as there's only one term in the denominator and your numerator and denominator are within the same family of function, we should be able to split up and handle each separately. Same thing with this, right? This is not a rational expression per se, but numerator and denominator are both under the same category, family of functions. So with only one term, I can split up into individual fractions and then handle them separately, clean up separately, and apply individual rules for each fraction, for each term. Okay, so that's what we do if there's only one term. It doesn't matter what the degrees are. We're just going to split up into individual terms. Now here's the second example here. Now we're in the territory of more than one term in the denominator. So if it's more than one term in the denominator, you know that we're not going to be able to split up. Expansion is not going to be an option. But look at the denominator versus numerator. You see how the denominator is 1 degree higher than the numerator? Also here, don't worry about the fifth root. Look at the x cubed. The x cubed is 1 higher than the numerator. That is a potential indication that this will be a U substitution problem, because my U value has a degree that is 1 higher, which the derivative will handle nicely when it ends up trying to cancel out that numerator x, and it does. Here, the derivative becomes 9x squared. That x squared handles that numerator nicely. So if your denominator is higher than your numerator by 1 degree, that's an indication that we probably want to explore U substitution as a possibility. Okay, third option here. Okay. Look at the denominator, more than one term. But my denominator and numerator are either the same degree or my numerator is higher. Okay, so if my numerator is higher or they're the same degree, that's a potential for long division or synthetic division. Okay. Long division can handle both these problems, but synthetic can only handle this one because we need a linear term in the denominator. So anytime there's an x squared that shows up, we know that synthetic is out of the question. So we're able to go through synthetic here. We're able to go through long division here. Long division here works as well. But that's what we're looking for, right? Your numerator has a variable exponent that is the same degree, if not higher, than the denominator. Okay. Now, here's the last option, which we haven't gone over yet today, which we're going to do today, is more than one term in the denominator. But now my denominator has a higher degree, but it's very specific. It needs to be 2 or more degrees higher. Okay. So this is not quite U substitution. You see how U substitution, my degree is only 1 higher. That will allow that perfect match. But if my degree is 2 degrees or more in the denominator than the numerator, then that's a good fit for what we're going to do today with arctrig. Okay, this is going to be arctangent. We're going to talk about that. And this one here, don't worry about the square root. Look at the x to the fourth. X to the fourth is more than the numerator. It's higher. That difference is more than 2 degrees. And we know that this is going to be a good fit, not for any of the previous options, but for arctrig that we're going to see today. So that's a big picture in terms of deciding what rule to use, using the degrees to kind of help us narrow down our options. All right, so this is what we're going to tackle today. Okay. So first semester, we learned about arc-trig derivatives, arcsine, arctangent, arcsecant. And what we're going to do is we're basically moving backwards from these rules. There's a slight difference because instead of just 1, now we have a constant that may be other than 1. But we can see still some similarities, right? The ones involving square roots are going to be arcsine and arcsecant. The rule that doesn't have the square roots is going to involve arctangent. Okay. So we're basically just going to be applying and practicing these rules today. Okay. There's 2 things I want to point out to you, and that's the A and the U and how to distinguish between the 2 of them. Okay. So here's the distinction. Your A value is going to be the constant. So if you're looking at 2 terms and you don't know which one is the A and which one is the U, the A has no variable in it. That's the constant. And the U is the variable expression. Okay. It has a variable in it. It could be 2x, it could be x squared, it could be x minus 3. And that's how you distinguish between the A and the U value. Because we need to be able to know which is which to decide between the rules that we're using. Okay. So our initial goal is to match, try to look at the problem, try to identify the rule that is a best fit. And once we're there, then we need to be able to locate what is the A and what is the U value. And there's a very specific way that I want us to do it that will ensure that we don't, that minimize the possibility of choosing the wrong A and U value. Okay, so let's look at number 1. Okay, I'm going to go down my options, my checklist. Expansion is out of the question. There's too many terms in the denominator. U substitution is not a good fit because my denominator has a degree that is too high, right? If I find the derivative of x squared, it becomes 2x. There's no x in my numerator to cancel out, so that's not a good fit. Long division, synthetic, not an option. But now I look at the x squared, that degree is higher than the numerator by 2 or more, so we know that may be a good fit with an arctrig, and now we got to decide which is a better fit under this arctrig umbrella. Okay. I see a square root, so that narrows down my option. I know it can't be arctangent, it's either arcsine or arcsecant. And the next thing that's going to help me out, I'm going to look at my first term inside the square root. Okay, I'm going to mash this up. Notice that x squared is showing up first. we know that is related to the u because it's not a constant, it's a variable. And the only thing that has a variable showing up first is my arcsecant, because my arcsine has the a coming first, and we don't see that showing up here. So we know that we're going to be targeting after this arcsecant to match up. Okay, so we have an idea what we're going towards, and now the next step is identifying the u value and the a value. Okay, so what I want us to do is I want us to rewrite the problem, but the denominator, I want us to put it in this form. You're going to have parentheses squared minus parentheses squared. Okay. If we do this, we can ensure that we don't pick the wrong a and u value. Okay, so this is what we're going to do. We're going to fill this in so that this overall expression is going to be equivalent to what we started with. So what can I put inside the parentheses so that this is the same thing as this? Okay, just x, right? No changes, looks like not much adjustment there. Okay. And so whatever is inside the parentheses with the variable, that's our u value. Okay, so now we know exactly what our u value is. Next up, what can I put inside the parentheses so that when I square it, I get a 9? 3. There we go. If you always do this, if you always start with this process, you won't pick the wrong a or u value. Now, what's inside the parentheses is your u and your a. We know our u value is the variable, so u must be x. We know the a is the constant, so a must be 3. And now we're just going to go through use substitution. We're going to identify what we found, and we're going to work towards making our problem look exactly like this. Make sure that there's no loose ends. Make sure everything is tied up. Make sure if there's a coefficient that we keep track of it. And once we get a perfect match, then we can jump into the rule and replace a and u with the appropriate values. Okay, so let me list out what we found. A is 3. U is x. And now we're going to find the derivative. Du dx is just 1. Looks like we're not going to have any coefficients to keep track of. Dx equals du. Okay. I'm going to start replacing the parts necessary to match with my rule. I'm going to push the 5 out in front as well. So 5 is just a coefficient. Dx gets replaced with du. The u is the x, followed by u squared minus a squared. Okay. If I cover up that 5, I got a perfect match. So I know I'm ready to apply my integral rule. So my integral rule requires the 1 over a and a u over a inside the parentheses. But we don't want to forget about that 5, so that 5 is going to have to be part of our answer as well. So I'll write down the 5 first. Followed by 1 over a. My a value is 3. Arcsecant. Absolute value of u over a. So absolute value of x over 3. Plus c. Do a little bit of cleanup. Make that 5/3. All right. Any questions so far? Okay, so let me summarize the steps that we did. We look at a problem, we had make sure that it falls under an arc-trig umbrella. We look at the form, try to identify what rule is the best fit. Next step, we get our denominator to show parentheses so that we can fill those parentheses in with the appropriate value without changing the problem, so that we can pick out our a and u value appropriately. Next step, go through use substitution, convert everything in terms of a and u, And once everything is filled in, we should be able to keep track of coefficients that needs to be part of our answer. And then we just follow the rule, replace the a and u with what we found at the beginning. Okay. All right, number 2. Integral of 1 over 4 plus x minus 1 squared. Let's go down our options. Power rule, not an option, too many terms. U substitution, my degree is not favorable for that. Long division, synthetic, that's out. Now, if I FOIL this out, I will get x squared. So denominator has a degree 2, numerator has degree 0. My denominator is 2 or more than my numerator in terms of degrees. So maybe an trig. Okay, so what do you think would be the best fit for this one amongst these 3 here? Yeah, arctangent, right? There's no square root, so we're limited in our options. We know it's going to be arctangent. Okay, let me put the arctangent rule here so we can have it easy access. Okay, so we know we're targeting arctangent. I'm going to get that denominator to be in the form that is most helpful. So we always do this. We always put parentheses squared. So we're not picking the wrong a and u value. Okay, let's make some adjustments here. What can I put inside the parentheses so that after I square it, I get a 4, 2. Double check, 2 squared is 4, that's good. Here, my form is already as a parentheses squared, so I can just copy down what I have. There we go. Now I want to point something out here. The rule says a squared plus u squared, but sometimes those may be flip-flopped, right? So just make sure that you understand. You can easily tell what is the a value. It's the constant. Your u value is the variable. So if they're flip-flop, just make sure that you're double-checking, making sure that you're assigning the correct variable to the correct value. All right, so we said our a value is 2. Our u value is x minus 1. Now we're just going to go through u substitution. And piece by piece, we want this problem to look exactly like this rule. If there's any coefficients that we're keeping track of it. And then once we get that match, we can jump into our rule. Okay, 1 in the numerator, dx becomes du. A squared plus u squared. So looks like I'm matching up perfectly with my rule, but there's no coefficient to keep track of. So I'm just going to jump directly into my rule. Okay. 1 over a, arctangent, u over a, plus c. All right, questions with the process? Okay, number 3. Going down our checklist, too many terms in the denominator, not power rule, u substitution, my derivative of my u value will not pair up nicely with the numerator. Long division is not an option, synthetic is not an option. Now our last option, notice my denominator has degree 2, my numerator has degree 0. So my denominator has degree 2 or more than the numerator. I know our trig might be a good fit. Okay, so look at how this is arranged here. How do we see square roots, right? So we know we're choosing between arcsine and arcsecant. which one do you think is a better fit?
Arctangent.
Okay, because why arcsine? Good, right? So the first term that you see, which is positive, is the a value is 7, and 7 is a constant, right? So that's how we decide, right? If you're dealing with square root, look at the first thing that pops up inside the square root, the positive term, and that will help you decide which rule to use. Okay, so I'm going to copy the arcsine rule below. And we're going to work towards this rule. Okay, so as soon as we identify the rule, we're going to try to get that denominator to be a little bit more helpful to us. So parentheses squared, but now it's minus, right? Minus parentheses squared. All right, we need to fill the parentheses with the value so that we're not changing the overall. What could I put inside the square root? Sorry, inside the parentheses where if I square it, I get that 7. Okay, root 7. Okay. Double check. Root 7 squared gives me 7. We know we're good. All right, what can I put inside the parentheses where after I square it, I get a 16x squared? Yeah. So if we do this, we're always ensuring that we're taking the necessary steps so that we don't pick the wrong a and u value, right? Yes, question.
Are we required to do plus or minus for once?
No. The reason why is because we only do plus or minus if we're dealing with an equation. If it was like y equals 16x squared, if you're taking the square root of both sides of an equation, then you have a plus or minus. But if it's just the principal value, if it's just an expression, we're only going to keep the positive. All right, any questions so far? All right, so if you do this, you're always ensuring that you're picking the a and u value correctly. Okay? We know what rule we're targeting, so I'm going to list out my values. My a is root 7, u value is 4x. Okay? It's important that we go through u substitution, especially for this, because we may have something that's going to come out of the derivative. So du dx equals 4. Okay, so I have dx equals du over 4. Now, piece by piece, I'm going to take my problem and replace every a and u that I find, replace dx. I want everything in terms of a and u, just to ensure that I have everything in this right place. Root 7 is a squared minus u squared. Dx gets replaced with du over 4, so we do have something that is going to be part of our answer, right? Push that out as 1/4. And if we look, now we have a perfect match. We can now apply the rule. Okay. 1/4 is going to be the first thing I'm going to write down. That's going to have to be part of our answer. Okay. Arcsine of u over a. There's no 1 over a with my arcsine rule, right? So I'm just jumping directly into arcsine. It's okay to leave radicals in the denominator. You can rationalize if you like, but there's no issues there. All right, questions so far? Okay, next page, we're going to do more of the arc-trig, but there's going to be some complexity that we're going to see on the next page. Next page, we're going to see that our denominator is not going to be quite set for us to pick the u and a value. The parentheses, even if we try to create parentheses, is not going to quite be in the form. So we're going to have to do a little bit of rearranging to get that denominator to show like what we see here on the first page. Okay, so let's look at the back. Okay, so here's example 4. We have dx over x squared minus 6x plus 13. Go down our options. Too many terms in the denominator, not expansion. Degree is not favorable for u substitution, not synthetic, not long division. But we see the denominator is degree 2, numerator is degree 0. Denominator has a degree that is 2 or more. So we're looking at our trig. No square root, so we're looking at arctangent. All right, but here's the problem. The problem is that this is not easy for us to pick out the u and a value because we don't have the parentheses squared. Maybe with the 13 we can do it, but the x squared minus 6x, how do we get that into a parentheses squared? So what we need to do is we want to get that standard form into more of a vertex form that's more helpful. And the way we do that is we're going to complete the square. Okay, so we want to complete the square to get that denominator to be in the form where we can pick out the a and u value. That's the purpose. Okay, so we're going to treat this like a separate problem. And let me walk through the steps for completing the square. Okay, first thing is recognizing that we're in standard form. The a is 1, the b is -6, and the c is 13. We want to cause this to factor nicely. So to factor nicely, we want to find an ideal constant that will cause that to happen. So I want to find that value. I don't know what it is yet, so I'll say plus space. Okay, I'll move the 13 over, but whatever number I find, I'm going to immediately subtract it because I don't want to change my overall expression. Okay. So whatever number I find, I can immediately subtract it, and that's going to still be the same thing as what I started with. So once we have that in place, we got to fill in those spaces. What goes inside those spaces is this formula b over 2 squared. That will ensure that our trinomial can factor nicely. Okay, what's our b value?
6.
Yeah, okay. I'm going to say -6, but it doesn't matter because we're always going to get a positive out of it. But I'll just say -6 over 2, which is -3. -3 squared is 9. So we're going to fit 9 into both spaces. This will ensure that our trinomial factors nicely. Okay, questions so far? All right. Now let's focus in on these 3 terms here. Multiplies to be 9, adds it to be -6. What does that factor to be? Yeah. They're both going to be -3s, right? And that's important because now we can get that to be a binomial squared, and that's what we want. We want that u value to show us parentheses squared. And then the 13 minus 9 combines to be what? Plus 4. Now, take a look at this. We started here, and now we're here. These are the same things, but this is a lot more helpful to us because we're moving towards picking our a and u value easier than here. Okay, so that's the whole purpose, trying to get that denominator to help us find the a and u value that we need. Okay, I'm going to reset, rewrite my denominator. So we're closer to where we want to be, but right, let's make sure that we follow through with the procedure, right? Let's get the entire denominator to show parentheses, 2 sets of parentheses squared. Okay, my first set of parentheses is already good to go. I know my u value is going to be easy to find. Okay, what can I put inside the second set of parentheses? 2, right? 2 squared is 4. Okay, if we do this, we can ensure that we're not picking the wrong a and u value. Okay, next step, we're going to work towards our rule. So let's identify our a and u value, go through u substitution, make sure everything matches. Okay, dx gets replaced with du. U squared plus a squared. Perfect match. No coefficients to keep track of, so we're ready. 1 over a. Arctangent of u over a plus c. Let me write this a little better here. Okay, questions? Okay, let's practice with another completing the square problem. But let's cross out number 5. This is more complex than what we need to be able to do. So let me change this to a problem from the textbook. So if you guys can copy this down here. Number 41. All right, go down our options. Expansion, too many terms in the denominator. U substitution, not a good match in terms of degrees. Not good for long division, not good for synthetic. So finally, we look at degrees. Denominator is 4, numerator is 1. Our denominator is higher than the numerator degree by 2 or more. So looks like we can maybe have a try with our arc trig. So we know if we want to use our trig, it's going to have to be what? Yeah, that arctangent, right? The denominator is not going to show square root. So, but we see that we have standard form. Our degree looks a little high, but this is still factorable if we can find a nice c value for us to factor. So we're going to spend the time to complete the squared here. Okay. Get the spaces to show up. Okay, fill in those spaces with b over 2 squared. Okay, what's our b value? Initially it's 2, right? And then it becomes 1, right? Okay, my b value is 2. 2 over 2 is 1. 1 squared is 1. So we filled our spaces with 1. Our first 3 terms should factor nicely. What multiplies to be 1 and adds up to be 2? Just 1, okay. But we got to be careful here. We're starting with x to the 4th, so we need to have x squared to begin with. But you're right, plus 1 and plus 1. Okay, which factors nicely to just, or which combines nicely to be x squared plus 1 quantity squared. 2 minus 1 just gives us 1. So we started here, and now we're here, which is a lot more helpful to us. Okay, reset. Get that denominator to be rewritten. Okay, I know I'm going to be matching with my arctangent rule. Let me put this right here so we can see it. Let's get the parentheses to show. Get that denominator. Get into the habit of just always doing it. So looks like 1 squared is still going to be 1, right? So there's my u value, there's my a value. Looks like we need to do a little bit more work here. That x is not going away just yet, so we're hoping that after u substitution, we can take care of that x, and we're able to make our problem look exactly like this rule. Okay, so a value is 1, u is x squared plus 1. All right, piece by piece here. I'm going to keep that x. My denominator, though, is going to become u squared plus a squared. But my dx becomes du over 2x. So what happens from here? Okay, good. X's cancel out. Yeah, we got to keep track of that 2, right? That 2 is coming out as a 1/2. So that's an additional thing that's going to be part of our answer. But outside of that 1/2, we have a perfect match with our arctangent rule. So I'm just going to follow what the rule says, replace a and u, but don't forget that 1/2, I want to put that first so I don't lose track of it. 1/2 times 1 over a, my a value is 1. Looks like that's not going to change much. Arctangent of u over a plus c. Clean this up further here, drop the 1s. Any questions? Okay. Yep, that's all I have. That's gonna end our new topic for this unit, and we'll start review on Monday. We'll do a couple of solving differential equations. We'll revisit slope fields, some word problems, and also revisiting some of the different integral rules. I hope to get back your quiz on Monday as well. A couple of reminders. If you're taking the Chapter 4 recovery test on Monday, I need that recovery assignment turned in to Teams by tonight. I'll be available in help session this afternoon. Your recovery test is either 7:15 or 4:30 Monday. Let me know which time you want to take it so I can assign that test to you. And then our Chapter 5, 6 test is going to be next Thursday. So we have Monday through Wednesday to review. All right, any questions? All right, have a great weekend, everyone. See you guys Monday.